Hello, everyone. In today's talk for the Games Accessibility Conference Europe 2024, we're going to be talking about exploring IRIS and Fonttik and the influence of accessibility tools on video game development. First of all, though, we want to share an important disclaimer. As one of our tools is a photosensitivity analysis solution, we want you to know that this presentation is completely safe to watch. Even though we're going to be talking and showcasing risky and problematic cases, we have ensured that everything shown on screen is safe for everyone, so you can safely continue watching. In terms of agenda, as the title of our talk already hints, today you're going to be exploring with us IRIS and Fonttik, two of EA's open source accessibility tools. So you get to see the influence that this type of solutions can have on video game development. And then we'll transition into IRIS and Fonttik, as in what they are, how they work, and more importantly, how you can use them already in your projects. But first, some quick introductions to tell you who we are. Blanca.
Hi, everyone. I'm Blanca Macazaga. I'm a software engineer at Electronic Arts, and I've been working for the past 4 years in both tools, the tools that we're presenting today. On Fonttik as a developer, and on IRIS, both as a developer and its own creator. So I'm very excited to be here presenting the tools to you all.
And I'm Carolina Cruz, Technical Product Manager. I started working at Electronic Arts a little over a decade ago, but it was nearly 2 years ago where I had the opportunity to dive more deeply into accessibility, getting to working, overseeing these two tools. And same as Blanca, I'm super excited and happy to be sharing the tools with you today. Now we're going to start the presentation. First, we have the accessibility tools in gaming. We wanted to give you a little bit of an introduction. As we all know, video games are becoming more complex and immersive, and the challenge of checking in-game accessibility increases, and not everything can be manually checked. Having available solutions that can check for different accessibility-related concerns plays a very important role, and this is where accessibility tools like IRIS and Fonttik come into play. These open source libraries allow for multiple uses and implementations, such as being able to integrate it in your workflows or even automation possibilities, giving anyone involved in the development process the opportunity to assess, analyze, and fix any potential problems before the games reach the final players. The first tool that we're going to be sharing with you is Fonttik. We all know that playing a game also implies being able to navigate it. And with Fonttik, our main focus was checking for text legibility. By detecting and recognizing the screen text, the font size and text contrast can be measured, which has allowed us to identify areas where players may not be able to distinguish important or critical text, like, for example, user interface hub, main menus, usernames in multiplayer modes, etc.
Take it over from here. So how does Fonttik work? Well, Fonttik is a tool that analyzes both videos and images. They analyze most media. For every image or video that's being analyzed, it will run the text detection backend so that we can detect which are the areas of the screen that have text, so that then we can extract the pixels that compose the text to be able to calculate its font size, and then also be able to extract the pixels that compose the background, just run the background of the text, so that we can calculate the contrast ratio between text and background. With this way, we can check the text legibility. Now, in practice, this is how it looks like. We have an image, which is an example of these subtitles in that space. And we see that for every word in the subtitles, we have a rectangle that surrounds it. This is the result of the text detection backend. So let's go for the nice word. In the next two images, we see that we have the pixels that compose the nice text and that are in white, and the surrounding and the rest of the background is in black. And then we have another one which we see that we don't have the pixels of the text in white, but only the pixels that are surrounding the text, and the rest of the background is black. This is the two processes that I've mentioned before. So we get a text box, we threshold it so that we can extract the pixels that compose only the text, and that we can now adjust the text box to get the text height. And then we expand those pixels, we expand that mask, so that we can do the same procedure and get also the background. Because once we get that expansion, we can subtract the pixels that compose the text and get only the ones that are composing the surrounding background. with this mask later on, what we can do is that we can use them to mask the pixels of the original image so that we get the luminance values of the text pixels and then also the luminance values of the background. And with this way, we can calculate the contrast ratio. Now, we're going to show how to use the console application for Fonttik. So if you go to our GitHub repository, you can also just download it from the releases. We have already pre-built it for Linux and Windows. I already have it downloaded on my computer. So I'm going to go and open my command line and analyze some content. So you can just, for Fonttik, you can just send over a media path with an image or video, or you can even send a folder where you can put multiple files over here and Fonttik will analyze all of the content. I already have my test folder with the dead space example. I'm going to analyze it. We have more command line arguments, but if you want to know more about it, you can check the GitHub repository. So we have the results already, and we're going to go for it. So we have the dead space image that we can quickly check it out. We have no text boxes over here in the subtitles. And if I go to the output results, I see that I get two images, one that's called contrast checks and another one which is called size checks, and two JSON files named the same. Let's check out the contrast checks. So if I open the image, we see the same one as before, the content that's been analyzed, and we see now we do have the rectangles surrounding the words that have been detected. And next to each, we also have some numbers that indicate the resulting contrast. Since all of these are above 4.5, all of the content has passed. These criteria, you can change it in the configuration files for the tools. Both on IRIS and Fonttik, you can change all the criteria if you wish to. And if I open this JSON file, what I will see is I will see all the results from the text boxes that have been detected with their dimension, with their coordinates, and with the result. So if it was a pass, which in this case, all the content passed, or if it was a fail. We have the text that is empty because we're not running the OCR. But if we wanted to recognize the characters, we could turn it on, and they will be seen here the text that was detected as well, as in the actual word itself. And that was it. This is Fonttik. As you can see, Fonttik makes what would be a rather manual check much more comfortable.
And now we move on to IRIS. IRIS's idea was born out of the desire of reducing photosensitivity risks in games and have an easy-to-use tool that could clearly mark all areas that could pose a risk or discomfort to our players. We're all familiar with the standard disclaimers in media that caution that certain TV episodes, movies, or games could induce health problems. Warnings like this were added as a consequence and solution to a well-known Pokemon episode that was aired in Japan back in 1997. This episode contained certain flashes that affected many of their viewers, taking around 700 children to the hospital due to mild to severe reactions to these flashes. It was this moment that led to the creation of certain guidelines in the audiovisual world, as it brought to the forefront the impact and the effect that certain patterns and flashes could have on viewers. Nowadays, data has shown that at least 5% of the 50 million people worldwide with epilepsy are photosensitive, in addition to many other people who experience symptoms triggered by exposure to certain kinds of flashing lights.
Now, how does IRIS work? So IRIS is also a tool that analyzes media, but in this case, only for videos. It analyzes videos frame by frame, and for every frame that's been analyzed, it runs through the detection models so that we can generate and collect data that allows us to detect the photosensitive areas of risk. And this way, we can check the accessibility of the video. So in the next slide, I'm going to show a few frames from the infamous Pokemon video that Carolina mentioned, because for the demo, we're actually going to be analyzing this content. Obviously, I'm not going to be showing the video, but I would like everyone to kind of see what the issues were with it. So the issue was with the Pokemon video was due to flashing. Now, flashes are defined as the pair of opposing changes, either in luminance or in red saturation. So meaning that it is either an increase followed by a decrease or a decrease followed by an increase. In the 3 frames that we see over here, we see that in frame 1, we had predominantly a red saturated background, and moving to frame 2, it's a predominantly blue background, and frame 3 is the same one as frame 1. In this section of the video frames were alternating between these frames. So frame 1, frame 2, back to frame 1, back to frame 2, and so on, until the entire screen was actually flashing between red and blue. Now, these moments from passing to frame 1 to frame 2, for example, that would be a transition 1. So we had frame 1 is, as again, mostly red saturated. So the value of the flash threshold for red saturation was being surpassed and reached. And then also for the flash area, because now the criteria that we have in IRIS is that if you reach 25% of the screen display or more, which in practice is 25% of the video area, if you reach that and you also reach the red saturated threshold or the luminance threshold, then you will be having a flash transition. So from frame 1 to frame 2, that would be a transition. And then from frame 2 to frame 3, that would be a transition again. So that decreased from frame 1 to frame 2 and increased from frame 2 to frame 3 that we were mentioning in the flash definition. So it's those opposing changes. So because of this, it was constantly flashing. Obviously, flashes can also occur, like the transitions of a flash can also occur through multiple frames. So we accumulate and track all the variations throughout the videos so that we can see those gradual increments or gradual decreases through videos. So next, we're going to check how to analyze content on IRIS. So I'm going to go again to my folder over here and open again the command line to run IRIS, which is also available in the releases of GitHub. For IRIS, you can just run the executable file, and it will, you don't have one created, it will create you a test videos directory, or you can just send the media path as well. I already have the Pokemon video in the test videos directory, so if I just run it, it will analyze the content. Now, it checks out that, gives us some information. So we have like the Pokemon video was open, the FPS of the video, which is important because the flash criteria in IRIS, which is based on official guidelines such as E2R and Ofcom, although you can modify the parameters yourself if you wish to, is based on the fact that only 3 flashes per second is allowed. So the FPS, the frames per second in a video, plays an important role to be able to be tracking these changes. Now, we also have a total number of frames, the resolutions and such, and we can see the progress of the analysis. It's a very short video, so it was very fast. Now, we see the result is that we had a flash fail, and thus the video result was a failure. It did not check out, it did not meet the criteria for photosensitive epilepsy. If we go now to our results folder that has been generated, and we go to the Pokemon folder, which is the result of the video, we can open this framedata.csv. Now, this CSV file contains all of the collected and generated data by IRIS. So we can see stuff like some columns for the frame index, the timestamps, and we can see also that we have things like the average luminance that was calculated for each frame, and the flash area luminance that was also calculated during the variations of each frame, one frame to the next throughout the video. And the good thing about this is that it means that we can use all of the information to track the incidents that occurred in the video and thus be able to fix our content. We can also use line graphs to be able to understand better how the evaluation of the incidents occurred. So we check out the red transitions, which were the biggest issue in this video in particular. Again, a transition, you need 2 transitions to have a flash. So if we go over here, for example, we can see that we were having 20 transitions per second. So at this moment, the video was flashing at 10 flashes per second, which is far away from what the criteria permits. And with this, we can see the entire evolution through the video. It's important to note that when we have the transitions moment, like that moment in the line graph or in the data, it means that we have 20 transitions at this moment up to 30 frames before. Because since we're checking for the criteria to see if we're flashing at any moment at more than 3 flashes per second, then what we need is to be able to track all of the variations, all of the incidents in that 1 second time window. The criteria also states that a continuous flashing between 2 flashes per second to 3 flashes per second could be harmful, which in practice means that if we were to be having flashes for around 4 seconds around those values, then that would be an extended flash failure. We have more of the information on these details on the GitHub repository as well. We also have the luminance frame result, for example, or the red frame result, which allows us to see exactly which frames have passed and which frames have failed the check. So a 0 would be a pass. A 1 would be what we call a pass with warning, because it means that the transitions were between 4 and 6, so 2 flashes or 3 flashes, which is useful to see if our content could potentially have an extended failure. A 2 would mean the extended flash failure, which is very useful to be able to check which areas have failed, as we would not be able to see that in the red transitions or luminance transitions graph or data. And a 3 would mean a flash failure. We also have information over here for the pattern detection columns. So we have things like the pattern area, the pattern frame result, and the detected lines. When we're analyzing for patterns, what we'll be doing is we will extract and filter out the pattern area that has been detected, so that then we can get its actual area size respected to the video, and also the number of lines, so that we can determine if it passes the check or not. And this is it for IRIS.
And this is the end of our talk. Now that you have seen IRIS and Fonttik in action, you can use them for your own project. Both tools are open to everyone, and both GitHub repositories are also collaborative projects, so feel free to add and share any suggestions or ideas to them. We hope you enjoyed the chat and both demos as much as we did. Thanks a lot for having us.
Thanks a lot for your time.